All right. So we're going to finish up a couple of slides that we didn't get to last time, and then we'll get into the new stuff for the review, and then we will talk about a couple of problems on the exam that in general, the class as a whole didn't seem to score too well on. So I just want to make sure that everybody knows what those answers are before they go into the final exam on Wednesday morning? Wednesday morning at 8 a.m. So let's look at number 6 here. So it asks, what would be the stereochemical classification of the major product of this reaction, where we're taking an alkene and we're reacting it with HBr. What kind of reaction is this, first and foremost? It's an addition, and we're going to add HBr across the carbon-carbon double bond in what kind of fashion? Markovnikov. Well, not anti, right? But in a Markovnikov fashion, right? And so in doing so, will we end up with an R enantiomer, an S enantiomer? Will it be achiral or will it be racemic? I got an achiral, I got a racemic. So you eliminated 2, right? We eliminated the fact that it can't be the R or the S, and why is that? Pardon? Well, that's true. It's not a substitution. But our starting materials are achiral, right? And we can't generate one enantiomer or the other in a reaction like that, right? So we know it can't be A and B. So it's either going to be an achiral product or it's going to be racemic. And right now I've heard 50-50 C and D. So it is achiral. So when you look at it, the hydrogen is going to go to the carbon with the most hydrogens. The bromine will go to the other carbon of the carbon-carbon double bond, assuming no rearrangements, right? It goes through a carbocation intermediate. But on this carbon, we will have 2 substituents that are identical, and on this carbon, we will have 2 substituents which are identical, and therefore, it's achiral. Question 7, which statement about these Fisher projections is correct? Anybody for C? It is D. 1 and 2 are diastereomers. Let's go through and look at all the answers. A, 1 and 3 are enantiomers. 1 and 3 are actually identical because 1 is what kind of compound? It's a meso compound. That's right. It has chiral centers, but it has a mirror plane of symmetry. So it and this actually are the same thing, right? So they're not enantiomers of one another. B, it says 2 and 4 here are identical. They are not identical. What are they with respect to one another? Those are enantiomers. 2 is a mesoisomer. No, and why is it not a mesoisomer? That's right, we have no mirror plane of symmetry. And 1 and 2 are diastereomers. That's in fact true because we have changed one of the stereocenters from whatever to whatever, right? And so they are not mirror images of one another, but they are isomers, so they have to be diastereomers. Don't forget, in these Fisher projections, right, where the lines cross, that's our chiral center, right? And what does that mean? The point lies in the plane. The things that are horizontal are coming towards us, and the things that are vertical are going back, right? So don't forget it. All right, there is no final quiz. All right, so for the review today, we're going to talk a little bit about nucleophilic substitution, elimination, the electrophilic addition, carbonyl compounds, and some synthesis and analysis. So this is kind of the second half of that ACS study guide. And again, copies are available. Our secretary's not in her office this morning, so you may have to get it on Monday if you haven't purchased one yet and you want to. So One of the nice things about the ACS study guide is it has these little one-pagers that really kind of give you an overview of the different things that you need to know going into the final. If nothing else, study these one-pagers out of this study guide before you come and take the final. Yes, the book's this thick, the study guide's about that thick, and you can even condense it down to these one-pagers. This will help you refresh the things that you need to know. At this point, okay, you should be studying a little bit of everything. But come Monday and Tuesday, you really need to be focusing on the things that you know well. You're not, Tuesday afternoon, you're not going to teach yourself all the stuff that you don't know. But you need to come into class knowing the stuff that you know, and you need to know it well so that you can get as many points from that as possible, okay? So the nice thing about these little one-pagers, they're kind of like little roadmaps. So it talks about the substitution reaction, right, gives an example, talks about the transition states. This would be what kind of a nucleophilic substitution? That'd be an SN2 type, right? And here we would have a SN1 type, so it puts all that into, condensed perspective. And then, of course, it also talks about elimination reactions. And so very important on these one-pagers to review all of that information, again, before the final exam. So let's jump right in and talk about some stuff. So, question 1. The reaction of benzyl bromide with azide is shown in the box. When the benzyl bromide concentration is constant and the azide concentration doubles, the reaction rate is observed to increase by a factor of 2. When the azide concentration is held constant and the benzyl bromide concentration doubled, the rate of the reaction doubles. What is the correct rate law for this reaction? It is D, and we know that because this is just a typical SN2 reaction, right? So we know that both species are going to be present in the rate equation. If you look at all these other things where you have, squareds and to the 4th power, if we doubled something, it's not going to just double the rate, right? I mean, it would go up quite a bit more than that. Question 3 here. What is the structure of the reactant that would yield the 2 products shown? It is C. What kind of reaction is going on? Yep, it is a substitution, but what kind? It is SN1, and why is it SN1? Okay, so we have a pretty highly substituted alkyl halide, right? But what do I know about the products? What did I tell you about SN1? It always competes with elimination, and so we're seeing both substitution and elimination. That is usually a telltale sign that you're going through some type of SN1 reaction, okay? So in this particular reaction, the leaving group leaves. That generates the carbocation right there, which can either be intercepted by the methanol to make the ether, or it can eliminate a hydrogen to make the alkene. Okay? Question 7. Which alkyl halide would you expect to undergo SN1 hydrolysis the fastest? Either D or A? It is A. What do we know? What is this question really asking? Which leaving group is the best? Because they're all the same molecule except the halogen, right? We know that tertiary alkyl halides will react faster than secondary, much faster than primary, but they're all tertiary here. So really it's just which one is the best leaving group, and we know the leaving group trend is as we go down a family, right? Fluoride is a horrible leaving group. Can it leave? Sure, but it's not very good, right? Chloride's okay, bromide's really good, and iodide is excellent, right? So don't forget those. Question 15 here. What is the major elimination product from the reaction shown? It is D. Why is it D? Zaitsev's rule? Zaitsev's rule would have told me that I would have eliminated this hydrogen, right? So nope, it's not Zaitsev's rule. What has to happen for this type of elimination to take place? What kind of elimination is it? Is it E1? Okay. What has to happen in an E2 elimination? How does the hydrogen and the bromine have to be aligned to one another? I think I heard it. They have to be antiperiplanar. Do we have any hydrogens as it's drawn antiperiplanar? We don't. But if we ring flip this, what you will find is that this hydrogen becomes antiperiplanar to that bromine, and then the elimination can occur. This is one of those examples where if you had something like this on the exam and you try to do it in your head, you will miss this question. What do you need to do? You need to build a model. You need to physically be able to look and see. Just because they drew it that way doesn't mean, unless it says as drawn, okay? These things can move. These things are flexible. They can take on different conformations and configurations, right? So if we ring flip this, what you'll find is that this hydrogen and this bromine happen to be antiperiplanar to one another. And so the deuterium atom, which is nothing more than heavy hydrogen, ends up remaining in the product. And that's why it appears like you don't get the Zaitsev elimination. Okay? Question 16, what is the major product of the reaction shown? Now there's one up there that you should be able to eliminate right off the bat. I wouldn't say I could eliminate it right off the bat. I wouldn't say that either. D. Why can we eliminate D right off the bat? Because it's between these two carbons, right? Or these two carbons. There's no leaving group there, right? So we can eliminate D. So from 1 to 4 chance to 1 to 3, it's better odds, not great, but you can still eliminate that one. Somebody said you can also eliminate A pretty readily, and I'll agree with that, but I wouldn't say you could immediately discount it. Why would you eliminate A pretty readily? Because it's not very substituted, right? So it's the least substituted alkene. Whereas when I look at B and C, I look at those and I go, well, those are both highly substituted alkenes, right? So if you eliminate A, you eliminate D, that leaves you with B and C, okay? Which one is it? It is B. Why is it B over C when both of them have equal substitution? Yep, that's exactly right. So it turns out that this hydrogen is actually more acidic because it's on the benzylic carbon, and when it eliminates, you actually get the conjugation of the whole system, right? So that's right. Question EA1, predict the major product of the following reaction. Eliminate possibilities for me. Okay? Any others that you can eliminate? A and B. What's the answer? It is D. What is this? It's just addition across a carbon-carbon double bond. Whose rule are we following? Markovnikov's. Do we have to worry about rearrangement here? No, because the initial carbocation we get is the most stable. We can't get a more stable carbocation, okay? Again, you're going to have that scratch piece of paper. I want to see problems being worked out. That's the only way to get these questions right, okay? How about EA2? What is the expected product from this reaction? Now eliminate two of them for me right off the bat. You can eliminate B and D. And why can you eliminate B and D, Anna? It doesn't seem right. That's true. But why doesn't it seem right? What are the products? Alcohols. Alcohols would be the addition of what across a carbon-carbon double bond? Water. Do we have water? We don't. So we're not even getting the right functional group, right? So in this case, we're adding alcohol across a carbon-carbon double bond, which gives us an ether, right? So we know we're not going to get the alcohols, as Anna said, so B and D have to be incorrect. That leaves us with possibility of A or C, and the correct answer is? It is C. Why is that? Let's see, what do we got? We got this. Proton's going to go to one of these carbons. It's going to go to the carbon that makes the most stable carbocation. Can I make a decision just based on substitution? I can't. But if the proton goes here, I end up with that carbocation. If the proton goes here, I end up with this carbocation. Which one is the most stable? This one, and why? Well, not charge separation, but you're close. I can draw a resonance structure for it. I can't draw a resonance structure for that one, right? So this carbocation is the most stable. It's the one that gets trapped by the methanol, and the correct answer, of course, is C. Question EA3. As shown in the equation, which set of reagents will convert the alkene into the alcohol as the principal product? It is C. Why? Let's go through this. Water and proton will add water across a carbon-carbon double bond. But in this case, what would happen? I'd have a carbocation rearrangement, right? Because the proton would go here, I'd get a secondary carbocation, which then would rearrange to the more stable tertiary. So yes, it'll make an alcohol, but not that one. So THF, BH3 followed by peroxide and base. That would give anti-Markovnikov. The proton and the OH would be here. This is what? That's the oxymercuration, demercuration, which gives us the Markovnikov alcohol without rearrangement because we have no carbocation. HBr followed by base. HBr would add across, or it would try to add across here. You'd get the carbocation, you'd shift, and then you'd get a tertiary carbocation, which the bromide would trap, and then the base, all it would do is another elimination. So it won't work there. EA8, what is the product of the reaction of E1-phenylpropene with peroxybenzoic acid? Eliminate two of them for me. I can eliminate A and B. And why can I eliminate A and B? Because I know that peroxy acids add an oxygen atom across a carbon-carbon double bond, right? So A is out of the question, B is out of the question. That leaves C and D. Which one's the correct answer? D. And why is D the correct answer? That's right. So if I look at my stereochemistry here, right, I know the methyl and the aromatic ring are trans to one another, and they are trans to one another in this molecule. Remember, peroxy acids add the oxygen atom to make an epoxide in a concerted fashion. So whatever the structure of the alkene is, that relationship is maintained in the epoxide that we form. The double bond here to make this product would have had to have the methyl group and the aromatic ring cis to one another, not trans to one another. Okay, so peroxy acids will react to make epoxides. My favorite peroxy acid, of course, was MCPBA. That's one I always used as an example. But all peroxy acids will do this, at least all of them that I know of. Okay. Question 10. What is the major product of the Diels-Alder reaction shown? Let's eliminate D. And why are you eliminating D? Because it's complicated? That's right. What do we know about a Diels-Alder reaction between a diene and a dienophile? It forms a six-membered ring with a pi bond in it, right? Unless it's a carbon-carbon triple bond dienophile. But here we have just a carbon-carbon double bond, right? So it can't be D. We're not going to get two pi bonds in the ring. What else can't it be? Can't be C. And why can't it be C? Okay, we didn't form a six-membered ring, right? And we know that Diels-Alders form a six-membered ring. So that's going to leave A or B. It is B. And why is it B? They are endo. This is also an endo. But if you look at this, the CO2CH3 is on this carbon, and the methyl's on that carbon, same as here. But if you look at this, these are how with one another? And they are, that's right, and here they are, that's right. Question Na2. Arrange the ketones in order of decreasing reactivity towards cyanohydrin formation with potassium cyanide and hydrogen cyanide. Which one of those would be the most reactive? Why would 3 be the most reactive? Correct. And so with that, we can eliminate what? Okay. Which is the next most reactive? Okay. And so C is the right answer, right? Why is 1 more reactive than 2? That's right. So you're looking at electronic steric interactions, and so the CF3s, very electron withdrawing, make this carbon of the carbonyl more electropositive, more electrophilic, more readily attacked by the cyanide anion, and then between these two it's all sterics. Good. Question 3. What is the principal product of the acid-catalyzed reaction of cyclopentanone with ethylene glycol? What is cyclopentanone? It's a ketone. What is ethylene glycol? It's a diol. What happens when you take 2 alcohols and react them with a ketone in the presence of acid? What do we get? It doesn't get weird. We get an acetal. Which one of those is an acetal? A is an acetal. B is an acetal. C is an acetal. D is not. So we can eliminate D. Do we preserve the ketone when we make an acetal? No. So we can eliminate B. So it's either A or it's C. Which is correct? It is A. Right? And so you form this cyclic acetal. Why would we want to do that? That's right. It's a good protecting group. So you can put it on and you can take it off pretty easily with just some water, right? But yeah, so it protects the carbonyl of the ketone. You can then do some other chemistry that you want that might interfere, and then you can remove it and get your ketone back. Question 9, what is the product of the sodium borohydride reduction shown to the right? What does sodium borohydride like to reduce? And so the answer would be? Sodium borohydride likes to reduce aldehydes and ketones. LAH likes to reduce everything, right? Carboxylic acids, aldehydes, ketones, nitriles, amides, a whole gamut of things we talked about. Lithium aluminum hydride can usually reduce it. Okay. Question EE1. Consider the hydrogen atoms attached to the 3 different carbon atoms labeled 1, 2, and 3. Rank the attached hydrogen atoms in order from most acidic to least acidic. 2 is the most acidic. So given that, what can we eliminate? A and C. What would be the next most acidic? 1. And why? It's alpha. That's right. So D is the right answer. Right. 3 would be the least acidic proton. What would be the product of this reaction? What are we reacting? 2 aldehydes. What's the name of this reaction? Aldol. Aldol is giving me what? Or that can dehydrate to alpha beta unsaturated, right? So can we eliminate based on any of that information? What can we eliminate? A, we can eliminate B, and we can eliminate C, and the answer is? Yeah, this is actually a mixed aldol. It did dehydrate, so this will attack. You get the beta hydroxyaldehyde, which then eliminated water to give the alpha beta unsaturated aldehyde.
So in like cross aldol, where you don't have an alpha hydrogen, that's where the alcohol goes.
Yep, that's right. That's exactly right. Question SA1. What is the major product of this reaction sequence? How are we going to do these sequences? One step at a time. So don't focus on the end product. Let's just look at that first arrow. What is that reaction? Nope. It's not a reduction. Sodium amide is a strong base. And so what's it going to react with? The triple bond or what? The hydrogen on the end carbon here, right? What's the pKa of that hydrogen approximately? In the 25 range, right? What's the pKa of this about? Mid-30s. Yeah, that's pretty good. So what am I going to get as my first product?
I'm going to get that carbamide.
That's right. So first product is going to be C6H5 and did they use sodium? Yeah. So there's my first organic product. What's going to happen in the next step? Okay, so it's an SN2 reaction, and what is that, a propyl bromide? So it's SN2, and we're going to form a carbon-carbon bond. Let's just write propyl. Okay? What happens if we take that product and now react it with hydrogen in the presence of Lindlar's catalyst? It's going to reduce the carbon-carbon triple bond to a double bond with what kind of stereochemistry? It's syn addition of hydrogen, so it will be a cis, right? So we will end up with a cis alkene. And so the answer is? A. A is the correct answer. So knowing that we had hydrogen in Lindlar's catalyst, we knew it couldn't be B or C. B would be the product if we used just hydrogen and palladium, or hydrogen and platinum, or hydrogen and nickel. C, we would have gotten C if in the last step we had used what kind of reducing agent? How did we get trans alkenes by this reduction? Wasn't Lindlar's. Wasn't another guy. D. I. S. S. Dissolving metal reduction. Remember, sodium or lithium and ammonia was the dissolving metal reduction. It would take a carbon-carbon triple bond, and you would end up getting a carbon-carbon triple bond and get a trans carbon-carbon.
So if you had palladium, that would reduce it all the way to the alkane?
Yep, you'd get B. Question SA2. What is the product of the reaction sequence? So what are we going to do in that first step? Acetal of the aldehyde and protect it, right? All right. What are we going to do in the second step then? Oxidize the alcohol to a what? Okay. Yep. Everything oxidizes primary alcohols to carboxylic acids except PCC and the Swern oxidation, which we didn't talk a whole lot about, but PCC was our go-to. Everything else we think of as like Jones reagents, and they will oxidize alcohols to carboxylic acids. The last step, what happens? Well, not the ketone. The aldehyde. And so the answer is, there you go. You okay? SA5, which of these reactions will produce isopropylamine? Shown over there on the right. Where are we at? Why can't it be D? There'd be an extra carbon. Why can't it be A? Ammonia doesn't add across carbon-carbon double bonds, does it? If it did, it would work, but it don't. Why can't it be C? Because we'd end up with one too many carbons, right? C will work to make an amine. Your potassium cyanide displaces the bromine. Then you reduce the cyanide to an amine. Here they're using hydrogen and platinum to do that, but you'd end up with too many carbons. What kind of reaction is B? Reductive amination. You make the imine, that imine then gets reduced. They're using hydrogen and platinum. But what was the reagent that we talked the most about? Sodium cyanoborohydride works really well. What reagent did you all use in lab to do this? When you did the Eschweiler-Clark? You used formic acid. That's right. Yep.
How would you get that isopropyl group from that?
So you're starting off with this. The ammonia reacts with it, and we get an imine, right? And then you just add hydrogen across the carbon-nitrogen double bond, and you end up with the product. Does that make sense?
Yeah, I drew one for you.
It's just not what?
It's just not like one of the CH3 2 carbons.
Yeah, it's just CH3 connected to that one CH.
They're separated, right?
Yeah, so this is CH3 CH, NH2. That's just what they drew up there. Yeah. What is the major product of the reaction shown here? It is B. And what's the name of this synthesis?
Gabriel.
That is the Gabriel synthesis. Very good. What reagents can remove the phthalimide? Base and water, heat, also acid and water and heat, or hydrazine, right? Good. All right. So just a couple of questions that had below a 60% success rate.
What is the structure of hydrazine?
Hydrazine, NH2, NH2. Question number 1. We had and then I gave a bunch of reagents. What kind of reaction is this? What are we converting from what to what? It's an oxidation. We're going from a ketone to a, okay? This is the haloform reaction, right? What you needed was sodium hydroxide and iodine in excess. So that was D, was the correct answer there. Jones reagent will, there's no functional group here for it to oxidize. It leaves carbon-hydrogen bonds alone, right? Jones reagent, you would need an alcohol here to even oxidize it. So Jones reagents oxidize alcohols, so it wouldn't mess with the ketone.
Do they oxidize alcohol?
Yes, but there's already an oxygen there, right? On the functional group that you're oxidizing. Because if you actually look at the mechanism, the aldehyde with Jones reagent converts to the hydrate, and it's that OH that gets oxidized further to the carboxylic acid, to form the carboxylic acid. So I'm going through a lot of pages here. Question 18 was the student choice, and it was which of the following reaction sequence would not result in a carboxylic acid in the final product. So A had an aromatic ring, and the first was acetyl chloride, aluminum trichloride, followed by MCPBA, followed by sodium hydroxide and water. And of course you have to assume workup where appropriate. And so this would actually give you a carboxylic acid, right? Because you go through the ester that gets hydrolyzed to acetic acid, actually. Okay. B, you were starting off with this aldehyde. No, this aldehyde. You were reacting it with ammonia and HCN, followed by H3O+. This is the what synthesis? We talked a little bit about making amino acids. This is the Strecker synthesis, and so it's going to make an amino acid, which is, by definition, a carboxylic acid. C, you're starting off with a phenol. You're reacting it with acetyl chloride. And then you're using aluminum trichloride and heat. What's going to happen in the first step? Yeah, and we're going to make an ester, right? We're going to make an ester with an aromatic ring. What happens in the second step? It's going to rearrange, right? That's the freeze rearrangement. And you'll end up with a ketone. No carboxylic acid. So this ends up being not able to form a carboxylic acid, and so it's the correct answer. All right, 28, last one. A student places 0.1 moles of sodium acetate and 0.1 moles of acetic acid into aqueous solution and dilutes the solution to exactly 1 liter total volume. What would be the resulting pH of this solution? What's the equation I need? I know that pH is going to be equal to pKa plus the log of A minus over HA. Well, there's my A minus, there's my HA. The log of 1 is always 0, so I know that the pH must be equal to the pKa, right? We're talking about a carboxylic acid. What's the pKa range? 4 to 5-ish, right? And I gave you A was 6.2, way out of the range. B was 9.9, way out of the range. C was 2.5, far too low. D was 4.7, and E was 1. So D is the correct answer, which is the pKa of acetic acid. Yeah, the pKa is the same for both species. Right, it's 4.7. Yep. So I told you all you could use a calculator, but I made all of those problems to where the ratio was always 1, so all you needed to know was log of 1 to 0. So pH equal pK plus log of A minus over HA. All right. So do people want a review session before the exam? When you want to do it? Tuesday? When? After 4:30. You have a final? 5-ish? 6-ish? All right, 6 o'clock Tuesday. Look for my email.